I think we've got a good number of people here. As people come in, it's okay. But yeah, let's get started. So for this first half of this review, we're going to talk a bit about atomic structure. A lot of the basis of organic chemistry 1, organic chemistry in general, is just understanding how atoms come together. They form bonds, how they form those bonds, what that looks like. So that's what we're going to cover really quickly first. Just getting started. The first thing, and I'm sure a lot of y'all remember this from Gen Chem, is the octet rule. The octet rule is simply most elements out there, most atoms that you're going to look at, you want them to be surrounded by 8 electrons in that outer shell to stabilize the molecule. There are some exceptions. You won't see them as often in organic chemistry. What you're more likely to see are carbon, oxygen, and nitrogen. It's important to remember that these molecules all follow the octet rule. Please don't change those slides. And one thing especially to remember is you're going to be dealing with a lot of, okay, if we're not able to not change the slides, I may have to just share my screen really fast. Give me a moment. So we've got this review, we're looking at atomic structure, and that octet rule, we're going to make sure that any of these molecules, any of these atoms, they have only 8 electrons in the outer shell. For example, carbon, you should never see more than 4 bonds on a carbon molecule, a carbon atom. You may see less, and it'll be charged, but if you see 5 bonds on a carbon, that should be your first indication that something is very wrong with your structure. The same goes, you'll see that a lot of these atoms also prefer a certain number of bonds. Carbon is most stable when it has 4 bonds, oxygen when it has 2 bonds, and it has 2 lone pairs out, nitrogen when it has 3 bonds. What you'll notice for all of these actually is that these preferred number of bonds are based on minimizing that formal charge, making that formal charge 0. So how can we calculate the formal charge? In order to do that, we can use this formula that y'all see here. Don't know if you can see my cursor, but formal charge is equal to the number of valence electrons minus the number of non-bonding valence electrons, which are just those like lone pairs. You're going to count each of those individual electrons that are not being used for bonding. And then you're also going to subtract 1/2 of the shared electrons in bonds. So the way I like to do it is I like to first check what group an element is in on the periodic table. That typically helps me figure out how many valence electrons. For example, I know that carbon has 4 valence electrons because I believe it's in group 14. And based on that, I can say that, okay, my V value is 4. I subtract my non-bonding valence electrons, which I can just count those electrons and those lone pairs. And then I like to just count bonds. When you count bonds, each bond is equal to 1/2 of 2 like shared electrons, just because they represent 2 electrons. So you can look at the examples we have here too. Take a look at those. This first one has an oxygen, which has 6 valence electrons traditionally. In this case, we see 6 non-bonding valence electrons, and we see 1 bond, so we can subtract that out. And formal charge is a great way to stabilize your Lewis structures, to check stability as well. A lot of the time, we're trying to minimize formal charge, especially on atoms like carbons. More electronegative molecules, or more electronegative like atoms, such as nitrogen and oxygen, are more willing to take on a formal charge than your carbon. So you're going to at least try to put that formal charge elsewhere. Okay, here we are. So just a couple periodic trends to note as well. We talked a bit about electronegativity. You'll notice that electronegativity moves to the right and up top. And we like to use something called a mnemonic called BEAR or bean. You'll learn bean later. Right now, it's important to remember that on your top left, you've got basicity. Atoms that are trending towards that top left side of the periodic table tend to be more basic. They're more willing to accept a hydrogen, accept a proton, and donate electrons. Versus you'll see on the bottom right, atoms trending that way tend to be more acidic. They tend to be more willing to give away or to accept electrons, give away a hydrogen. So just looking at that. And then you'll see a greater reactivity trending to that bottom left. And those are some just good metrics, some good ways to compare acid bases, also to consider a lot of bonding, a lot of what can carry charge better. Typically, more electronegative atoms are better able to stabilize the charge than less electronegative atoms, which is why we prefer not to have charges on our carbon. And then moving on, electronegativity, again, also helps us sort of look at bonding. You can use it, first of all, to check for polar versus nonpolar bonding. If you have a more similar electronegativity, something that's next to each other on the periodic table, you'll choose that to be more nonpolar versus a larger electronegativity difference. If you're given values around 0.5 to 2.1 is polar, and also I don't have it listed on this PowerPoint. If you have a very large electronegativity difference, such as an atom in the halogens column and in the group 1 elements, you'll, like when you see a bond between those two, such as like hydrofluoride, that will be an ionic bond. Some other things to note for bonding. One thing that you're going to start seeing now that you're in organic chemistry is stereochemistry. You want to make sure that you're checking stereochemistry. It's really important that you recognize that there's a possibility that molecules that you're looking at could be a mirror image of each other. You have to really understand how things rotate, how they're supposed to look. I really recommend having a model kit on you while studying for these exams. Also, just some basic details for that are when you're looking at a perspective drawing, you're going to see anything on our lines is going to be in the plane of the page, versus our dashed line should be going out behind the page, and our wedge line is coming towards us from the page. So it is a bit frightening at first, but I promise they get easier. It's a really good diagram. I really like them. And in addition to that, it's also important to consider different kinds of bonds. You're going to be looking at both sigma and pi bonds. And this is a really important distinction to make. Our single bonds, our first bond that each, like 2 atoms will make with each other, is a sigma bond. Those can be using hybridized orbitals. However, pi bonds are those additional bonds. They form multiple bonds. So if you have a triple bond, your first bond will be a sigma bond, but then your second and third bond will be pi bonds. And in order to form those pi bonds, we need p orbitals that are orthogonal to our other orbitals, such that they can sort of reach out. And let me see if I can draw it out. Let's see. Oh, that's not a good color. I'm going to draw it out here. You're going to have something where they can form a bond where we've got these atoms, they've got like some stuff around them, and we're going to form pi bonds up here, such that they're coming out, they're perpendicular, those p orbitals are perpendicular to those bonds, and those help form those additional multiple bonds that I was just talking about. And you'll see why those are important in a moment. And yeah, let me just erase. Okay. But first, let's also talk about some intermolecular forces. This is also important for bonding. A lot of the time, we think about covalent bonding, But we also have to consider the forces that act between molecules, intermolecular forces. So when you see an increase in those forces such that they're more adhesive to each other or cohesive, it increases the boiling point and melting point because they make it harder for, because now that things are more cohesive, they make it harder to elevate the temperature to create a rise in that atomic that atmospheric pressure, no, that pressure, vapor pressure above a molecule. So that's something important to remember. In addition to this, it's also important to remember that we can use those intermolecular forces to understand how things dissolve. Solubility increases with both polarity and with the kind of bonding energy. So let's take a look at those really quickly. First, you've got hydrogen bonding. That is the most strong intermolecular force you have. You'll see they form, or the most strong that you will look at. You'll see that they typically occur on carbon-fluorine bonds, carbon-nitrogen, and carbon-oxygen bonds. What they do is they allow us to create sort of this extended, we are able to put these charges on our hydrogens, and on those electronegative components of those hydrocarbons, or not hydrocarbons, but on those molecules, such that our electronegative part becomes somewhat negatively charged and our hydrogen becomes somewhat positively charged. And it's attract, in this case, the negative and positive charge come together, they form hydrogen bonds. And while they're not covalent bonds, they do help bind together molecules and keep them more cohesive. Next, we've got dipole moments. Those are formed in polar molecules. What you're going to be looking at is anywhere where we see that difference in electronegativity, a larger difference in electronegativity, you'll see that the electrons are drawn away from the less electronegative molecule to the more electronegative molecule. So in this case, if you look at HCl, those electrons are being drawn away from that hydrogen to the chlorine. And that can really cause those opposite ends again to attract to each other because we create these charges on those molecules such that, like, chlorine has a negative charge, that hydrogen has a positive charge, and now they also attract to other HCl molecules. Finally, just looking at the most basic, we have London dispersion forces. For those, they're weaker than dipole-dipole movements, but they do involve instantaneous dipoles. They're spontaneous. And these increase with surface area. So one example that I've seen very common is if you look at geckos, for example, they have very large feet. Like, they're spread out a lot. And that's because they use London dispersion forces to move up walls. They use those to walk up walls. So if you need an image in your head, that is one that you could have. And in this case, it simply is just the larger it is, there's still going to be some amount of polarity within a molecule, even if it's not entirely polar. Next, we have hybridization. And for hybridization, this also gets really into some of that stuff I was talking about with sigma bonds versus pi bonds. We have three forms of hybridization that we cover generally in OCHEM. They are sp3, sp2, and sp. sp3 molecules tend to have four sigma bonds or 4 sets of lone pairs, or any combination of that. And they are tetrahedral. They have bond angles of 108.5, and no pi bonds can be formed because there are no p orbitals free to form those pi bonds. sp2, you'll see that we have 3 sigma bonds, and then there's one p orbital that is left over that can be used to form one pi bond. So you'll see sp2 a lot of the time when you see a double bond, or when you see a resonance structure where an atom will become double bonded. in one of those resonance structures. And the same goes for sp. You're now going to have 2 sigma bonds, and they have the potential of forming 2 pi bonds. You'll often see this in triple bonded molecules. Again, it can be either sigma bonds or lone pairs that are involved in those like hybridization. It's really just you have to consider how many p orbitals do I need to leave free to form pi bonds. That is the main question being asked of you in hybridization. Some other important things to remember, you really should learn those bond angles, sp3 108.5. For sp2, it's 120 degrees, and for like those sp, it becomes 180 degrees. Another important one to remember, I don't think I put them on the slide, is when you have a p orbital such as the one shown, let me see if I can use a laser pointer, yeah. If you have a p orbital such as this one, this will be considered 90 degrees from any of these sp2 or like any of these hybridized orbitals. So you may see questions on your exam where they will ask you, oh, what is like the bond angle between this lone pair that's in the p orbital with like a sigma bond? The answer to that will be 90 degrees. It's important to remember that those p orbitals are orthogonal, they're perpendicular to these hybridized orbitals. That's why we can form pi bonds, and it's something really important to remember. Don't go using like 120 degrees or like 180 degrees. That's incorrect. Okay. And we've sort of covered some of the basics about atomic structure. We're going to move on into some more O-chemistry territory. We're going to look at resonance. For resonance, it's important to remember, this is again something that you may have seen in your Gen Chem class, but what's really important to remember about resonance now is that it represents the delocalization of electrons. When we are seeing a resonance structure, it's not just the one, it's all of the possible structures that can be formed. So at any moment, an electron can be at different points within that structure, right? So a molecule is the average of its resonance structures, and because of this, we can see that charges tend to be not simply on one atom, they tend to be on multiple. So you'll see something that looks almost like a half charge on different atoms. Some things to remember again are carbons cannot have more than 4 bonds. When you're building those resonance structures, do not ever like create something where your carbon has 5 bonds or 6 bonds. It does not work. And then another thing to remember is only electrons are moving. We're not moving anything else right now. You should only be moving those electrons when you're looking at changes in charge, like where charges are moving. And then in terms of choosing major versus minor contributors, we're going to see that some of the things we're looking out for, you're going to see are the same throughout this presentation. But when we're determining stability, we're going to look for as many octets as possible. Remember that octet rule. We're going to be looking for as many bonds formed as possible on carbon. The ideal number is 4. If you have a negative charge, put it on the most electronegative atom. Carbon will not be happy with it. And also something to remember is to minimize charges. You will just want to have overall less formal charge on each atom. If there must be one, it should be on that more electronegative atom, such as oxygen or nitrogen. And yeah, here's a look at some of those resonance structures we talked about. You can look at, these are some of the situations in which you will recognize that you need to do a resonance structure. The first is often the one that most students are able to recognize. It's the allylic charge. When you have a charge that is adjacent to a double bond, you can see that double bond move such that that charge is over here. In reality, what's happening is that we're seeing some electrons, those electrons being used here, move over so that we can create a pi bond here. and now there's less electrons here, creating that positive charge. And here, this is a really good visualization of a negative charge moving, where we see those electrons again be used to form a double bond, and we see these leftover electrons stay and form a negative charge. For one of our second cases, we also see anytime that you have a lone pair adjacent to a charge, that can also convert into a double bond, something important to remember. And same thing here. If we have a polar pi bond, such as something with an oxygen on it, ketones are really big on this one, you will see that that oxygen can take on another set of electrons, and we'll see a lone pair in a charge distribution. In this case, see, like, carbon's got a positive charge. It's definitely not happy. You would prefer this one where you have no charges on either of those atoms. And then finally, last one is just conjugation. That's just your classic benzene. You're going to see those, like, where when two double bonds are adjacent to each other, they have only one sigma bond in between them. That's where you can notice that that's a conjugated set of double bonds. It's the best example is benzene in this case. Yeah. And moving on, we also should look at, we're going to be doing a lot of stabilizing this unit. It'll be a lot of stabilizing in OCHEM in general. We're going to be, when you rank the stability of anions and cations, there are some things that stay the same. For example, resonance is always good when you're looking at the stability of a charge, because it means that that charge is delocalized. There's less charge per atom. And then you'll also see that really that's the one thing that stays the same. On anions, remember that's a negative charge on a molecule. You're going to see that they want to be on primary carbons. They want to be on carbons that are not attached to a lot of electron notating groups. They don't want to be attached to a lot of methyls. They want a lot of hydrogens. And they like primary more, and then secondary and tertiary. And you should really notice that, because on the other hand, when you look at cations, it's the opposite. They want to be on a more stable position where these methyl groups act as electron donors, and they are able to stabilize that positive charge more and make that central carbon atom closer to 0 in terms of formal charge. Also, for anions, you're going to be looking for that charge to be on the most electronegative atom. So again, you want it to be on like those oxygens, those nitrogens, and inductive groups in this case are good. You want inductive groups to pull away some of that negativity and help, in the same way as resonance, delocalize that charge. In terms of cations, you're going to be looking at, again, you want tertiary over secondary and primary. Resonance is great. And in terms of cations, you also want to maximize pi bonds. This means that there is greater electron density around it again. That's important. And inductive groups are bad in this case. They draw away electrons from an already positive charge. That is not great for a cation. Yeah. And then just based on that, resonance also has some effects on hybridization. Again, it's important to remember that it's not just when you see a double bond. You also have to consider cases in which resonance structures are forming pi bonds. So even though, say, this nitrogen is not originally involved in a double bond, we still have to give it sp2 character, sp2 hybridization, because it later goes on to form a double bond in some other resonance structures. We have to keep a p orbital open in order to allow that to happen. If it is not open, you can't like unhybridize and be like, oh, let me just pop out that p orbital really quickly. It has to be out the entire time. And yeah, so that's mostly what you need to recognize. They really create that overlap. This is what I was trying to draw out earlier, that you want to see those p orbitals overlap in order to create those pi bonds. Okay. And last for me is we're going to look at some IR bond stretches, and I'm going to pass it on to Justin in a moment as well. So we're going to look, one thing that they've added for y'all this semester is IR bond stretches. You're going to see more of this in organic chemistry too. I think it's great that you get to see these a little ahead of time. I know y'all have charts that you're going to use on the exam, but we're just going to point out some of the major points that you should look out for when you're identifying a molecule. So starting with just the basics, IR bonds well, IR is a spectroscopy technique that uses infrared light to create vibrations in bonds. This is typically used when we see some dipole-dipole moment. You're going to not be seeing a lot of nonpolar bonds, such as carbon-carbon bonds on benzene. You need to see some difference in electronegativity in order to see that vibration. And also something important to remember, again, for resonance is that resonance lowers that wave number. It shifts the bond stretch left to, or no, it shifts the bond stretch right to a smaller number. I apologize for that typo. So just starting with the basics, and here it's just sp3, sp2, and sp. You're going to look for first those sp3 alkane bonds, those basic single bonded carbons. They're going to have a stretch at 2850 to 2990. What's important to remember is they tend to be below 3000. And then our sp2 stretches tend to be a little above 3000. I really like these two to identify those that difference. If you're going to look at an sp2 bond, you can also identify that based on some of the bond stretches in the 1600s region. I generally don't recommend it just because you can get lost in a lot of details in that area. I would prefer that y'all look at just whether you're seeing peaks below 3000 or above 3000. In addition to that, you also have sp, so those alkyne bonds are a little interesting. You'll see them at you'll see them also around 3100 or around 3100 and so on. So they're a little later than like sp2 bonds. But the main one that you want to look out for on that one is you're going to be looking out for those double bonded, not double bonded, sorry, those carbon-carbon triple bonds. Those are not on this image, but they're going to be around 2100, like right where this line is. Something to note is that they tend to be below 2200 later on, and this is not a fact you need to know. When you look at cyanides, those also have carbon-nitrogen triple bonds. They are going to have bond stretches above 2200. So you're just going to be looking for a line over here. Next, we also have aromatics, and this is again where we see that resonance really take action and cause these carbon-carbon double bonds to sort of shift to the right to a smaller number. You'll see a peak around 1500 and 1700. Generally, yeah, like you have a very large peak around 1500 that should set you off. That's an aromatic. It's probably benzene for you right now. So that's one that's really important to remember. You can also look for these sp2, sp3 bonds. I recommend just looking straight at 1500 about. If you see that peak, that should be what sets you off. Yeah, and I'm going to hand this over to Justin. Justin, I can just continue scrolling through the slides for you. Just let me know if I don't.
Okay, sure, that works for me. Okay, so the next group we're going to talk about are the alcohols and acidic alcohols. So usually we can see an OH stretch at about 3300, and it's that broad sort of stretch we see in the bottom left. Now, when we have something, an acidic alcohol, like in a carboxylic acid, we see the stretch a little bit more towards the right in the 30 or the 3000 group. So OH structures are pretty easy to tell just because they're not pointy like other groups. So these are really good indicators about where to look for. Next slide. So now we're going to talk about the carbonyl groups, which are the most prominent spike we can see on an IR. They usually appear around 1700, and there's this long spike that happens. And so we see on the left that there's a carbonyl spike for a ketone. And if we remember, a ketone is just the carbonyl with just CH3 attaches. So this is going to occur at 1710. We also see a similar spike on the right, but this indicates an aldehyde, which is a carbonyl with one hydrogen attached to it. And so we know this is an aldehyde because at around 2700 and 2800, we see two sort of fangs right there. And so if you notice, we don't see these on the ketone side. We only see the sp3 stretch. So this is indications about how an aldehyde works. If we go to the next slide, or sorry, actually, could you go back one? One other functional group that fits in the carbonyl groups is the ester. And so the ester is the long chain right here. And so usually these will have higher wave numbers than ketones. So usually they'll be at around 1730. But the peak still looks the same. So when differentiating the two, it's important to figure out what number the spike is exactly at. Okay, next slide. So now we have ethers. So we see that there's an oxygen-hydrogen stretch around 3200, 3600. Not much we could tell from ethers just because there's not a lot of functional groups that we can differentiate. And the carbon-oxygen bond is in the fingerprint region. So for a lot of students, it's hard to recognize when we see an ether spike or it's just another spike. But we can tell that there's sp3 hydrogen bonds in the 2850 to 2990 region. And otherwise, you could look for the lack of groups, right? Because most of the time, they'll give you a formula, and then they'll give you this IR. So if you notice that there isn't any carbonyl spikes, but you have an oxygen, you might want to consider an ether. So that's how we can use the IR. We can use the information presented and what's missing from it. Next slide. So now we're going to talk about amides. So amides are, if you remember, they're the carbonyl group with the amine attached to it. And so this is showing around 1630 to 1690. They're a lot smaller than esters or ketones. Now, if we're going to talk about amines by itself, which is just the NH2, we'll see them at around 3300. And there's three types of variants. We have primary amines, secondary amines, and tertiary amines. So we'll see primary and secondary at around 3300, but how we can differentiate them is based off the number of spikes we can see in that region. So if we look at our diagram right now, we have a primary amine because we have two spikes. These two spikes represent the number of hydrogens the nitrogen has. So with the primary amine, it's NH2. So we'll see two hydrogens. If this were, say, a secondary amine, we would only see one spike. And for tertiary amines, we don't see a stretch at this region. So that's the basics of amines and amides. All right, how's everyone doing? I think we're going to start on our second half of this presentation. So we're going to go into really the heart of OCHEM, where we're going to talk about stereochemistry, isomers, naming, and the different types of projections. Is everyone back? Let me know in the chat if you can hear me. All right, so I'm going to begin my section. Okay, so let's go through the foundational knowledge of chemistry. So the first thing we're going to start off with IUPAC nomenclature, which is essentially how we're going to name hydrocarbons in your case. We're not going to go too complex, so we're just going to start off with simple line angle drawings. So the first thing you have to remember is you need to be able to memorize all these types of prefixes right here. So these ones are important for all the different types of chains we're going to talk about. And they're also good when you're going to be talking about side chains later. Because if I tell you what an ethyl chain is, you should know from your head that that means a 2-carbon side group right there. Right? So we know that because the F indicates there's 2 atoms. So it's useful for naming, and later it's useful for side groups. So let's talk about the rules of IUPAC naming. So the first thing we want to do is find the longest carbon chain with the most substituents. A lot of times you might see two carbon chains of equal length, but you're trying to maximize the number of substituents or side groups on that chain. Next, once you have this chain, you need to pick the number 1 carbon. And so you want to make this in a way where it decreases the numbering. And we're going to talk about that later with some examples. If you have multiple identical side groups, then you have to use prefixes. And so this is if you have 2 methyl groups, then you need to indicate that with a di prefix. Or if you have 3 ethyl groups, then it's a tri prefix. We also need to write out our side groups in alphabetical order. So that means that we have something like iso will come before, actually, scratch that. It'll be ethyl, iso, methyl. Had to double check. I did not know if E came before I. But yes, we have to make sure that these come in alphabetical order. If you have a ring system, you'll add the prefix of cyclo. So a 5-membered ring is called a, 6-membered ring is called a cyclohexane. Now, if numbering works in both the directions and you can't really differentiate, you should pick the one with more side groups. And if that doesn't work, then you can pick the order that works alphabetically. So now let's talk about some examples. So if we look at the molecule on the left here, first thing we're going to do is find the longest carbon chain. So we have the option of going this direction. We have 1, 2, 3, 4, 5, 6. So we have this option right there. We also have the option of going 1, 2, 3, 4, 5, 6. And so if you notice, this side group that's vertical has more substituents, right? So that means we're going to be using this side group as our main chain. So because we know it's 6, I'm going to say hexane. So now we're going to figure out which way do we want to go from. If we start at this side, we have 1, 2. Number 2 is methyl. If we start from this side, we have 1, 2, 3. 3 is ethyl. So because we reach a number faster, we reach number 2 before we reach number 3 on this side, we're going to start from this direction here. And so let's number that. We're going to have 1, 2, 3, 4, 5, 6. Okay, so now we have a methyl group here. We have an ethyl group because there's 2 carbons, and we have an ethyl group here. And so from our naming, we're going to say the ethyl groups, we're going to put those first because E comes before M. So we're going to write 3, 4, and we're going to indicate dimethyl diethyl. So now we can do the methyl, which will be 2-methylhexane. Okay, that makes sense. So now if we move on to the ring system here, we have a ring system, so we're going to say cyclohexane. We don't really need to worry about counting carbons because there might be a long carbon chain, like if we do 1, 2, 3, 4, 5, like that, but with the ring system, you count your ring as like the main source and you number based off that. Symmetrical, you can start anywhere, number 1. Oh, sorry. Okay, that's good. So we can pick this to be number 1 or this to be number 1, and we can go in any direction, right? So the reason we're going to pick this position right here is that it has more substituents than this number 1 right here. So we're going to number this as 1, 2, 3. And so we're going to say 3-methyl 1,1 dimethyl cyclohexane. Okay? Now, if let's say there was just another ethyl group here, we might be inclined to start right here because then they have the same number of side groups, they're the same length apart, so we're going to pick alphabetically because E comes before M. All right, good so far. So now we're actually going to go a little bit more into the cyclohexane molecule. So the cyclohexane molecule is important because it's not actually seen as our line angle drawing. We see it as this chair conformation right over here. And so an important property is that it can perform ring flips to change its conformation. There's 2 types of positions on a cyclohexane. We have the axial position, which point up and down, and we have the equatorial position, which skews outward horizontally. Now, what happens during a ring flip is that the axial positions will swap into equatorial positions. However, this doesn't mean that an up axial position will now become a down equatorial position. All it's simply going to do is become an up equatorial, right? So because the direction of the bond doesn't change, even through a ring flip, a molecule will remain cis or trans because of the double bonds are going to remain the same. If we're talking about stability, this is highest on the equatorial position. This is due to a decreased 1,3 diaxial interactions in the ring strain that we have here. So if we look here, we can see that this ethyl group is interacting in a 1,3 way with these 2 hydrogens here, because this ethyl is on an axial position. When you do the ring flip, it's going to be turned into an equatorial position. So now there is no interaction, and so this is going to be the favorite group. So now the question is, how can we convert between a line angle and a chair diagram? So an important thing to remember is that wedges are going to indicate an up position, while dashes are going to indicate a down. So if we do our example here with OH, Br, CH3. What I like to do is I'm going to go around in a circle and say axial, equatorial, axial, equatorial. And so these are all up positions. So if the wedge matches, then that's an up. However, if it's a dash, it's going to be the opposite. You may have learned a different way of doing this, but this is the method I like to use. So we're going to move around. We have axial, equatorial. So because it's a wedge, this is equatorial up. Axial, equatorial. Because it's a wedge again, this is also going to be equatorial up. Axial, equatorial. The wedge would indicate equatorial up, but because it's a dash, this indicates an axial down. So now when we draw our chair structure, we can pick any position and just have to keep our distance the same. So we have an equatorial up position right here, the OH. 2 carbons away, we have another equatorial up position for the CH3. And then 2 carbons away, we have an axial down position for the bromine. Right? This makes sense? And so I could have done this any way, where I could have said these positions are actually down, and then it would be the reverse, but it would get you the other chair conformation. Because once you do the ring flip, then these become axial up instead of equatorial up, right? So you could do this any way you like, but as long as you keep it consistent, you should be able to get to the right answer. So now let's talk about stereochemistry. And so this concept directly ties with chirality. So what is chirality? Chirality is if a molecule cannot be superimposed on its mirror image by any combination. So that definition by itself doesn't make much sense, but we're going to explore that. For chirality, you need a chiral center, which is the carbon.
If I cut you off for a second, would you be willing to go back and discuss why you chose the certain parts as axial versus equatorial? Some people had questions about that.
Okay, so I'm basically like creating a system to go around where if I pick axial, if I start it, because I go alternating, or axial, equatorial, right? And I'm going to say that any wedges are going to be indicating the up or with. Sorry, let me rephrase this. Wedges are going to match my ring. So what I'm saying is, in this position, there should be an equatorial up. So because it's a wedge, I know, okay, that means it's equatorial up. In this position, the wedge should indicate equatorial up. But because it's a dash, it's going to be the opposite, in a down position. So because it's a down, it has to be an axial, because I said equatorial has to be in the up position. If we can also do it, try a different way. If I draw out the ring again, okay, so let's say wedges mean up. So I'm going to say this is an axial up because it's a wedge. So because of that, the next up position has to be equatorial up. Because if you look at a ring, if we look over here, you see that it goes axial up, equatorial up, axial up, right? You never have 2 axial ups right next to each other because it's axial up or axial down. So the next up position should be equatorial. So the one right after that, if this is equatorial up, this has to be axial up, right? Because we can't have an equatorial up because it's this carbon here already. They're alternating. So that means CH3 is an axial up. So we go again, equatorial up, and then axial up. However, we notice that because it's a wedge, because it's a dash, we now indicate the opposite. So this transforms into and equatorial down. And this gives the same answer as the one I just had, but it's the different chair conformation. So we can now draw it as axial up, 1, 2, axial up, 1, 2, equatorial down, like this. And you can get the old configuration I had by a ring flip. Sorry, flip. And this happens because during a ring flip, axial and equatorial positions switch, but directionality doesn't change. Does this sort of make sense? Let me check the chat, see if I can.
Yeah, I think everyone sort of figured it out this roundabout. I think it's just a bit of a question at first.
Yeah, it's sort of confusing at first when you're trying to do it, but once you realize that you can, as long as you keep it consistent, you can do it anyway. Can I? Let me try. I usually have trouble drawing the other sided ring, so let me see if I can do this.
So is it okay to label, like, to start at any point as equatorial or axial?
Right. So as long as you're keeping consistent, right? So I could start here, and I could say this is axial up, right? I have to keep consistent the position and the directionality. So if I keep this as axial up, the next one is equatorial up, right? So that means this group is going to be equatorial, which hence matches the ring flip. Does that sort of answer your question?
Yeah, it does. I'm just trying to think through things in general.
Right. I'd invite all of y'all to just experiment with this and see if like doing a different position actually works. Right. The more you practice, the easier it'll become to realize I can start anywhere and it'll give me the same answer. So I'm trying to. Okay, so that's the other ring. So if once we flip it, no, I think that's the same ring. Sorry, I'm really bad at drawing the left-handed ring. So if it looks like this, essentially the OH goes here. 1, 2. This CH3 goes here, 1, 2, and the bromine goes there. So we see now in this position, it's equatorial up, equatorial up, equatorial up. Sorry, this is actually an axial down. That is my mistake. Okay, let me erase. So this is sort of how the ring flip will look like, where the directionality is the same, but we've just swapped the axial and equatorial positions. Does anyone else have any other questions before I move on? I'm looking at the chat right now. Okay, so there'll be some more practice in our review packet after we finish this. So you can work with your tutor like through the process. So for now, I'm going to move on to stereochemistry. And so the last thing we were talking about is chiral centers, where I said it's a carbon with 4 non-identical groups. So these are a part of a group of molecules called stereoisomers, where the molecules have identical bonding, but there's a difference in spatial layout. And so you learned of a priority ranking group that we had, where when you want to figure out R and S configuration, we're going to use the highest molecular weight. So if I have something like carbon with CH3, hydrogen, bromine, and OH, we're going to say 1 goes to the bromine, 4 goes to the hydrogen, 2 goes to the oxygen, and 3 goes to the methyl. And so this is because bromine has a higher molecular weight than the oxygen. We're going to be comparing the first atom connected, right? I had a question once where someone said, well, doesn't CH3 have a higher molecular weight than, I think, like, let's say OH, right? But the difference is that you're not comparing the CH3 group as a whole, you're only going to be comparing this carbon right here to this oxygen. So oxygen has a higher molecular weight than carbon, so that means it's given priority over carbon. So we'll have some more practice in the review packet exploring RNS configurations. So now let's talk about the different types of stereoisomers. We have enantiomers, which are mirror images that are non-superimposable. So what this means is that all chiral centers are going to be flipped. So if we want to draw out the RNS configuration here, we're going to say this is 1, this is 2, and this is 3. And so the reason I can differentiate is even though these are both connected to a carbon, this one is connected to an oxygen in the next bond, while this is connected to a hydrogen. So if the first atom connected doesn't work, you move on to the next atom connection. So because the next atom connection is an oxygen, it's going to have a higher priority. So we'll say 1, 2, 3, like that. Hydrogen is 4, and it's on a dash, so we're going to say S. For this one, we're going to do this. We're going to have the same priority. 1, 2, 3 is clockwise, and because hydrogen is on a dash, it's going to be R. So we notice that the chirality has flipped. So this means this is an enantiomer. With a diastereomer, these are stereoisomers that are non-superimposable, but not mirror images. So this means at least one chiral center is flipped. So if I do, for example, a Fisher projection, so I say OH, I'll say Br. The diastereomer would look something like this. So if we notice, only one chiral center changed configuration. This one right here. Meanwhile, the other chiral center remains the same. So this is now a diastereomer. This is not an enantiomer because they're not mirror images of each other, right? An enantiomer would be all the chiral centers have to be flipped. Under diastereomers, we also have cis and trans molecules. So these are also known as geometric isomers, but they fall under the same category. So if you're ever given a pair that's cis and trans, you have to realize that those are diastereomers. So our last type of isomer is going to be the meso. So this is a molecule with chiral centers, but because there's a line of symmetry, it makes the molecule achiral. So if we see here, there's a line of symmetry down here. So you know how non-superposable means we can't overlay them on top of each other, right? If you can imagine your hands. If you try to put your hands on top of each other, you always have the thumbs sticking out, right? But if your hands were symmetrical, then this wouldn't be a problem, because now, even no matter how you overlay them, it's still superimposable. So the big thing to look for is a line of symmetry. So if something like this, this is a meso compound because of a line of symmetry going this way. Okay? It has chiral centers. However, the molecule itself is achiral. That's an important distinction. So now we're going to get into projections. So projections are different ways of trying to help us show chirality in stereochemistry, because line angles sometimes aren't the best at doing this projection. So we have two types. We have the Fisher projection and we have the Newman projection. So to go from a line angle to a Fisher projection, we would say, well, first, this is an easy way for long chiral centers, right? Because each intersection here represents a chiral center. So now there's two types of positions. We have an up position here, and we have a side position here. So if something is in the up position, this is equal to, we can consider this as a dash. And the side is considered as a wedge. So when doing chirality, if you consider this hydrogen right here, because this is on a wedge, you have to flip the chirality. So we can say 1 here, 2, 3. So that looks like an S, but because there's a hydrogen on a wedge position, it's going to now become R. Whereas if I had something like this, hydrogen, OH, bromine, this would now be 1, 2, 3. So this would be equal to S, because the hydrogen is now in the dash position. The next projection is the Newman. So this is, you're viewing the bond in the 3D space from two chiral carbons, which is going to be a front carbon and a back carbon. And so this is useful to help us visualize the bond angles and any unfavorable steric interactions. The important thing for this one is that the most stable position for a Newman projection is anti, where the two largest groups are opposite of each other. So we'll see that example in our review packet. So now let's figure out how we can convert from a line angle to each of these projections. So a Fisher projection, what you're going to do is you're going to draw out your chiral centers like so. You're going to draw the two vertical bonds. So we see here that the vertical bonds are the ones that are going to be in plane without a wedge or a dash. So here it's going to be the CH3 bond. And right here it's going to be the ethyl group. So we can get those sorted. So for the side bonds, the safest way is to check chirality, because a common mistake is that you might want to say, oh, CN and Br are both wedges, so they need to be on the same side. However, this doesn't work all the time, because if I have something like this, OH, the correct Fisher projection is actually this right here. Because if you check the stereochemistry, these two have the same chiral centers, right? We're not going to change any chirality. We're only transferring it in a different view. And so this happens because the correct way to draw a Fisher projection is you have to look at it like this, where these two groups right here have to be pointing downward. So when you do this group will stay the same, but this becomes a dash instead. So now it matches this group right here. And so when you have complex molecules, it might be hard to sort of turn the molecule into this sort of shape right here. So what I advise you to do is instead to figure out the chirality and make sure it matches on these groups right here. So check chirality. For a Newman projection, there's a sort of shortcut we can use.
Can I interrupt for a second?
Yes.
Sorry, about the previous one. Why is it so? Why did like CN, for instance, like why did that change, or not CN, BR? Why did that change from the little triangle to the dash later?
Why did it change from a wedge to a dash?
Or yeah, a wedge to a dash.
So the reason is, like as I explained up here, we have to make sure that these groups right here are pointing downwards. So because they're sort of both pointing upwards, if you wanted to like convert it directly, you would have to draw it out like this, right? But once that happens, the BR actually now becomes a wedge, and the CN stays a dash, because you're bringing this upwards. You're like rotating it on its axis. Now, if you check the chirality before and after, you wouldn't have to like worry about this rotation, right? Because the chirality remains the same. And so we can do a simple check right now. So this is, I think bromine's heavier than chlorine. This would be 1, 2, 3, 4. So this R, I think that becomes S. And then we'd say 1, 2, 3, 4. So that would also be R, but because, well, this one's a little confusing because there's no hydrogens. Let me try a different molecule. Let's just say I'm going to do, okay, I'll do this one up here because I actually know the chirality. So this is 1, 2, 3. This is R because the hydrogen is on a dash. If we go over here, we see it's 1, 2, 3. It looks like an S, but because hydrogen is in this position, it becomes an R. So we see that the chiralities stay the same, even though it doesn't look like they're the same, right? Because over here, it's like, oh, we have two wedges, so the OHs should be on the same side. But that's not necessarily the case. Does everyone get that?
Oh, I'm sorry. I just have a question real quick. So I remember my TA said like, oh, if you're on the right, the wedges will be on the right, and the left side will be dashers on the left. Is that
right?
True?
That is not true for Fisher, but it's going to be true for a Newman. So we're going to talk about, like, for Newman, it's a lot easier with wedges and dashes, but for Fisher, that's not always going to be this case, right? Because if we can see right here that we have two wedges, but they're not on the same side, right? Does that make sense? And this is because you have to look at a Fisher projection sort of like you're looking at it from above in this direction. And the two groups need to be pointing downward, like so. So this might be a little confusing if you like to always like turn your molecules into this formation. So what I advise you to do is instead to figure out the chirality of this and match it over here. Okay, does that sort of make sense for everyone? Okay. Okay, so now I'm going to clear the board a little bit to make some room. So now we're going to talk about Newman projections. So for these ones, this is a little easier to match the wedges and dashes, where first you're going to find the up and down groups, which are going to be this group right here. These are the groups that are going to be staying in the plane. They don't have a wedge or a dash. So first you need to figure out on your first carbon is if that group is going to be pointing upwards or is it going to be pointing downwards. So we see here that this group is pointing upwards. So we have that as our reference. So next we're going to do is you sort of need to visualize from the eye and sort of know if the wedges are going to be on your right or on your left. So in this case, when you're looking at it from this direction, the wedges appear on the right side, right? Because wedges are coming towards you, so they're sort of right of this eyeball here. So we see that wedges, the hydrogen and the CH3 are going to be on the right. The dashes are the two hydrogens, so they're going to be on the left. However, if, for example, the test told you to look at it from this angle, now the wedges are actually going to be on the left side because you're sort of looking at it from the other direction. So because wedges are still coming out of the plane, they're going to be on the left side of this eyeball. And so that's what we see in our Newman projection. We see wedges on the left and hydrogens on the right. So if you want to simplify this, if you're looking at it from the left, wedges are going to be on the right, dashes are going to be on the left. But if you're looking at it from the opposite way, it's going to flip the orientation. Does anyone have any questions about that? Okay, I don't see any questions. So now we're going to talk about converting between Fisher and line angle and Newman in a line angle. So this is actually a lot easier than converting from line angle to Fisher. So first what you're going to do is we're going to draw the two chiral centers and their vertical groups. So in this case, we have this chiral center here and this chiral center here. So I would draw a bond like this, and then I would draw their vertical groups downward. So it's going to look something like that and look something like that. Because if you remember, this position up here is a dash, like from above, technically. So it's going to be pointing downward in this like upside down U shape, right? Next, what we need to do is draw it from this person here. So because these are going to be towards this person, I'm going to say hydrogen is a dash and OH is a dash. And likewise, hydrogen and OH are wedges, and Cl and Br are going to be dashes, right? And so this is a lot easier than trying to go from line angle to Fisher because now you don't really have to check chirality. You're just drawing it in this formation. But the important thing is you have to make sure that these two groups point downward, or else it will actually change the chirality. So that's a big thing about Fisher. The two end groups have to be pointing down, okay? With a Newman projection, first, what you're going to do is draw out the front and the back carbon. So let's do this example here. So we know there's going to be a front, there's going to be at least 2 carbons, right? So we're going to draw that bond. And next, we're going to draw the vertical positions because we don't have to worry about wedges or dashes. So it's going to look like this. Good so far? And so now we're going to see that since I'm drawing from the left, these are going to be wedges, these are going to be dashes. So we're going to have CH3 like that. And then hydrogen, hydrogen. Okay? Does anyone have any questions about converting back from Fisher to line angle and Newman to line angle? Okay, so Alan asks, why did the CL and BR change from wedges to dashes? Oh, okay. So what this diagram here is showing is that all groups, this is showing like on this side, the side groups are considered wedges, right? But this is from like a bird's eye view. Because if we remember, side groups are wedges and vertical groups are dashes. But that's not corresponding over here. This is actually how we look at it from the plane, from this perspective over here. So sometimes textbooks will draw Newman-Fisher projections in this way to sort of indicate that the side groups are wedges, but it's not like they're changing, it's just a different perspective. Yeah, like Grace said. So how do you decide which is which? So you take the perspective of this person right here, right? You're going to look at it from the left side. So once you drew out your OH, your aldehyde and your CH3, you're going to say, well, from the left side, if I'm looking at it directly on this way, the hydrogen and OH are facing me. So because they're facing me, that's going to be what? A wedge, like here. Exactly. And so because CL and BR are facing away from you, that's going to be the dash. Yes. The answer, it would sort of switch if you're looking at it from the right side. Because, so what you have to do, so I'll just do an example. Let's say we look at it from, whoops. Let's say we look at it from the right side. So I'll put a person here. So once we do that, I have to draw out my groups a little differently. So I have to say now the CH3 is over here and the aldehyde is over here, right? But now when I do this, I'm going to say, okay, Cl is a wedge because it's facing me. And Br is a wedge because it's facing me. And so this is going to be OH. This is going to be hydrogen, right? If you notice, I changed my wedges and dashes, but I also changed like my orientation of the entire molecule. Because now the aldehyde is on this side, whereas before it was on this side, right? So it's just a matter of perspective, which way you're looking at it. Okay, yes, let's check on the new Fisher. Are you talking about this molecule right here? Okay, yeah, let's actually show that, they're the same chirality. So I'm going to do this one right here. So we have bromine as 1, OH as 2, and this one as 3. This is 4. So it's going to be R, but because it's not the number 4 is on a wedge, we're going to say S. Let me check on the Fisher here. So we have 1, 2, 3, 4. So, okay, it's actually R. I was mistaken. It gets a little weird when the 4th group is on the plane, because now you have to sort of look at it differently. You have to sort of imagine it's like BR, OH, like that. You're looking at it from this direction. So in this case, it's easier to look at the Fisher. So what we see is that it's 1, 2, 3, so it's going to be R. Now if we move over to this line angle, if we're looking at it from this way, we see bromine, OH, like that. So it's 1, 2, 3. It's still R. I'm sort of like putting my eye up here. I'm looking at it from a bird's eye view. Okay. Does that make sense for everyone? Okay, can we do another example of the Newman conversion? Okay. Yes, we have time for that. Okay, so I'm gonna erase everything on this slide. I'll just give you a sec if you want to take a screenshot of it. Sorry, both are. I mistakenly said one was S, but they're both R in this case. Okay, so let's practice another Newman projection. So if I have CH3 Cl, and we'll say this is OH. Okay, so first thing I'm going to do is I'm going to draw my 2 carbons like this, because I know there's a front carbon and a back carbon. So on the front carbon, I know CH3 is going directly up. And on the back carbon, I know hydrogen is going directly down. So now we're going to say, well, if I'm looking at it from this direction, I notice that the Cl and the hydrogen are on my right side. So if they're on my right side, that means they're actually going to be wedges like this. Oh, sorry, that's the wrong one. So this is going to be hydrogen. This is going to be a Cl. And so this likewise, because these groups on my left side, they're going to be dashes. So bromine as a dash and OH as a dash. And so this is our new line angle. Okay, so that is interconverting between Fisher and Newman. I think that is the last slide.
Yeah. We did miss acidity and basicity ranking, so I may do that really quickly on the whiteboard. And then after that, we can break out rooms.
Okay. Just want to check. Does anyone have any questions on stereochemistry, converting, projections, any of that before Ria demonstrates ranking? How is the second diagram R in the last slide? I'm not quite sure which R we're talking about. Oh, for the line angle. Are you talking about?
Because we showed that it was S, but then you change your mind and put it back to R.
Yes, because I was looking at it the wrong way because I thought, oh, because the fourth group isn't on a wedge, that means it's S. But you're supposed to look at it from this angle because it's a little different when the fourth group is in the plane. So if you look at it like that, you can sort of see that bromine would be over here, OH would be here, and then CH3 would be this way, with the CH3 sort of like pointing in that direction in the back. So now it would be 1, 2, 3, or R. And so to make it like even easier to find, if we look over here, you see that it's going to be it's going to be 1, 2, 3, and because the fourth group is on a dash, it's going to be R.
Well understood. Thank you, sir.
Okay. And yes, like Ray said, that's what I used to do. I used to only make, I would make carbon with 4 different colors. And so I could just assign each color to a different molecule. It doesn't necessarily, I don't have to like necessarily create it each time. I could just say, okay, in this case, I'll just say carbon is fluorine. The red is fluorine, the green is CH3, and the blue is hydrogen. Yep, exactly. Okay, so if no one has any more questions about my section, Ria's just gonna take over for a second to explain acid-base ranking.
Yeah, let me just pull up a whiteboard. And yeah, I'm sorry, we somehow did not cover acid-base ranking like in the slides at all. But I'm glad someone brought that up, so we can definitely take a look at that now. If you saw the chat earlier, something I mentioned about acid-base ranking is it's essentially just you've got your acid, right? What we're going to be doing is we're going to be ranking the stability of the conjugate base. So we're going to rank the stability of, like, say, if I have an alcohol, we're going to be ranking the stability of this molecule over here, this conjugate base. Where we have removed that hydrogen, it's been plucked off. Let's say we've used like NaOH to do that. And we're left over with just like this anion. What we're going to be doing is very similar to actually ranking anion stability. I like to use an acronym for this called ARIO. It is ARIO. The A stands for atom, R stands for resonance, and I stands for induction. That O stands for orbitals. We're not going to discuss that right now, but it's just a good, it's good to know all of them. But I'll just cross this one out for now. Here. Okay. So we're not going to look at that one yet. But right now, the first thing you want to look at for that atom is you're going to be comparing 2 things. One, you're going to be looking at electronegativity. If you remember that chart I showed you all earlier, you're going to be looking at, if we have our periodic table here, we label it there. So we've got our bases, electronegativity, acidity. We can use this to find it. And actually, this is also where it becomes useful to use acidity ranking. So that A also comes in useful. We're going to be looking for atoms that tend towards this bottom right area. We're also going to be looking for one other aspect of this atom. We want a larger electron radius. So, for example, let's say that we have sulfur. Sulfur has, I believe it has 2 electron shells. So sulfur, it looks something like this, versus when we look at oxygen, it only has 1. So sulfur has a much larger radius than oxygen. even though it is technically less electronegative, because it has a larger electron radius, because I would say you'd see carbon, or not carbon, oxygen over here, sulfur is like somewhere over here. So sulfur is closer to that A, and because of that, you can say that sulfur is a better atom to have for acidity, right? So that first one is just, we're going to use atoms. We're going to look at electronegativity and electron radius. And I'm going to really quickly see if I can maybe not erase everything, but we're just going to go down the list for the rest of these. And I may erase things later. So atom, then we have resonance. That's pretty simple. It's just having resonance structures. You want to delocalize that negative charge again. You want to make this conjugate base more stable. We want this negative charge to be all over the place. So like a good example of that would be, say, if I had like a ketone like this, or even something that looks like, yeah, like a ketone like that, we can use that as we can use resonance to sort of create a resonance structure, which would make it more stable. And I'm going to clear this really quickly as well, and we're going to look at just induction last. We also look at induction, and for induction, yeah, carboxylic acids are more acidic, and that's because they have resonance structures. Induction is our last thing, and when we're looking at that, we want to have more electron withdrawing groups. We want to delocalize that negative charge, right? So for example, if I have, say, this alcohol, let's look at that again, and I have like a chlorine on this end, that chlorine is going to drag away some of those electrons this way, which means that when this becomes negatively charged, right, I'm gonna, e-learning is not my friend sometimes, but yeah, when this is negatively charged, it's going to delocalize that charge. It's going to try to drag it over this way, which is good. That creates a more stable conjugate base that increases reactivity of the acid. On the other hand, if you have a more electron donating groups, such as methyl groups, we're going to say electron donating bad. I have something that looks like this, where for some reason I've got like a negative charge, and then I have one over here. This oxygen's not happy. Why are we donating more electrons that way? We're making it more negative, and we want to reduce that negativity, right? So we want to say that, so what we're going to be looking for again is just, we're going to look for those atoms, resonance, and then after that we want to determine induction. So we're going to be trying to delocalize that electron, those electrons, that negative charge, and so we want inductive groups that would draw those electrons. They are highly electronegative to be attached to our molecule, right? And I think we saw some questions about like carboxylic acid. Absolutely, that is considered more strong. One thing that I also want to note for y'all is if you see a traditionally strong acid, like if you see a traditionally strong acid like say SO3, HSO3, this is going to be much stronger than even your like carboxylic acid. In OCHEM, we get really used to saying that carboxylic acids are considered very acidic, but you have to remember that anything that is considered a traditionally strong acid that completely dissociates, like you learned in Gen Chem, those are going to be considered more strong than most of the organic molecules we're looking at. So just a note to keep in mind. Are there any questions on this? I know I rushed through this a bit, so just want to see if you have any other questions on that. So if one structure has resonance, but has the negative charge on a nitrogen, but another has no resonance and has a negative charge on a fluorine. So first, we're probably not going to see too many. Actually, no, we may see some negative charges on a fluorine. I would say you would first go with that atom, simply because even if I had resonance and I had like a negative charge on like a carbon, it doesn't matter. Like, this is not really, well, it would depend. In this case, though, yeah, if it has a negative charge on nitrogen, and then, yeah, I would say you would prioritize, I would say prioritize resonance over the atom. But I would say that's also a question you should ask your professor. A lot of professors have different preferences for that. So we can only tell you what we know, but a lot of the professors are the ones who grade those tests. So do check with them. Which will be more acidic between fluorine and chlorine? You're going to be looking for the more electronegative atom in that case. I believe that's fluorine, so you're going to be using that one as more acidic. Okay, so, and someone just commented that Dr. Tran wants resonance first, so do keep that in mind. For everyone else who does not have Dr. Tran, be sure to like reach out to your professor at office hours or something. It's really important because we do have times where like professors have discrepancies. Peer tutoring really can't do much about that. So yeah. But any other questions before we move on to breakout rooms? I don't see any questions right now, so we're going to start heading into breakout rooms.
All right, so we're going to do some questions. So once this whole review session is over, you'll get an email about, you'll get an email to this recording and to the packet and the answers. All right, so let's start off with some cation stability. So if we remember, what we're doing first when we're ranking cations is we're going to think about any resonance they have, the number of what type of carbon they're on, whether it's like primary, secondary, tertiary, and any other electronegative groups that are going to support it. So from this, can anyone tell me what you think is going to be number 5, or what you think is going to be number 1? So I'll label this as 1, 2, 3, 4, 5. So just from looking at this, what do you think is going to be the worst stability? Can everyone hear me all right? Okay, number 5. That's a good guess. So so maybe this will be 5. Does anyone have any other guesses? So these are all going to be weak cations, but what's actually going to be number 5 is the first one here. And so you might be wondering, like, this looks like it resonates, but because this cation is directly on a double bond, this is highly unstable. We don't want cations to be directly on bonds. So if you ever see a cation like this, you already know that this is going to have the least stability. So the same way, we're going to prioritize resonance. So that's going to be this one right here. Because as we see, it has benzylic resonance and this allylic resonance right here. So this is going to be extremely stable. So the next one with resonance is going to be this molecule here, number 2. And so now between 4 and 5, which one is going to have a higher stability? They both don't have resonance, so this is just based off of the carbon. What do you guys think? Which one has more stability? Good. Number 5 has more stability because it is a secondary carbon, and cations prefer going secondary, tertiary, secondary, primary. So that's going to be number 3, and this is going to be number 4. Okay, good. So now we're going to rank the following compounds by basicity. And so if you remember basicity, this is directly correlating with, if I remember our periodic table, it's going to be up here, basicity, BR, right, our Bayer acronym. So basicity is, I like to think about it, how reactive the negative charge is. So we have a bunch of anions here. So the more unstable the anion is, the better it can react with. So the first thing is we're going to consider the molecule. Or sorry, we're going to consider resonance, right? Because like how resonance is good for stability, it's going to be bad for basicity. So this is going to be number 5. That's because this negative charge is resonating between the ring, between the benzene. So because it's resonating, it's stable, but that means it's not as reactive, right? That negative charge isn't going to be good to attack hydrogens away from an alcohol. So that's why that's going to be number 5. Number 4 is going to be the sulfur right here. That's because if you look at our periodic table, sulfur is going to be down here. So it's stabilizing the negative charge, which means it's bad for bases. Next, we have 2 oxygens and a nitrogen. We know nitrogen is going to be a good base because of the periodic trend. It goes this way. And these methyl groups here are known as electron donating. So because they donate their electrons towards a negative charge, it makes it like more powerful, more reactive. So this is going to be number 1. So now we have 2 options. We have an O- next to a chlorine, and we just have a regular O-. So in this case, what we're going to say is, well, what do you guys think? Do you think it's this O- with the chlorine or this O- just by itself? Which one's going to be a better base? Yes, 4 will be a better base. And the reasoning for that is this chlorine right here. Chlorine is an electron withdrawing. So because it's withdrawing the electrons away, it's making that negative charge more stable, and stability is bad for a base, right? Because we want really reactive negative charges. So this is going to be 3, this is going to be 2. Good job. So now we're going to move into hybridization. So we have 2 atoms here that we're pointing to. And so for N1, what is the hybridization for N1? And what is the hybridization for O2? I'll give you guys a couple of seconds to figure that out. Okay, good. N1 is sp2 because we see 3 electron domains. Now, what about O2? Yes, good job. sp2, sp3. Okay, so now the tricky question is, it says for the compound above, provide the following bond angle. So the first is the bond angle between this lone pair, the nitrogen, and the carbon bond. So can someone tell me what they think that bond angle is going to be between the lone pair? Right there. Good. Yes, it's going to be 120. So, Tram, you might be thinking that this lone pair is in the p orbital, but if we remember, if we draw it out like this, so we have one pair here, the lone pair is going to be in an sp2 orbital. And that's because we're using our p orbital to form a bond in this direction, right? Because the p orbital is being used for a bond, it can't occupy the lone pair. So the lone pair has to exist somewhere else. And so because it's an sp2 orbital, it's going to have a bond angle of 120 degrees. Now, what about the OH? What is its bond angle? Yes, 109.5. And so in this example, there's only, right? So once again, it's not going to be 90 because we said this is sp3. So that means it's 1s and 3 p orbitals, which means there's no free unhybrid p orbital for a lone pair to be in. It has to be in one of the sp3 orbitals. So because of that, the bond angle between sp3 orbitals is 109.5. Good. Okay. So so let's do the last one. Last part is draw all the resonant forms of the molecule. So resonance is just, we're going to try moving the bonds around. So if we move this lone pair down here, we get this resonance structure. Right? And if we so once we do that, this nitrogen has 5 bonds, which can't happen, so we need to move that up here. So that becomes like this. And so what we can also do is move this bond in this direction here. So now we have this structure over here. Sorry, it just came from there. Sorry, let me redraw that. What I actually meant was if we have this lone pair here, we can move this down right there to form the triple bond in that direction. And this goes back here. So now it looks like this. Okay, so that's how we essentially move the bonds around to form the resonant forms. It's all about moving electrons, moving lone pairs, and making sure that you don't break the octet rule. Okay. So if no one has any more questions on this page, I'm going to move on to the next one. I think if I move to the next page, it's going to erase the work. So I'll give you a second if you want to screenshot the work for a second. All right. Next up, we have name the compound. It's always fun. So if we remember our rules, first thing we want to do is figure out the longest carbon chain. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That probably looks like our longest. So it's going to be 10 carbons. So we say 1, 2, 3, 4, 5. This is carbon number 5. So this is an example of a complex substituent. So what you do is you'll say this is 5, and then we're going to also name this instead. So if we did that, we would say this is carbon 1, this is carbon 2, this is carbon 3. Let me expand that a little bit. So with the complex substituent, this carbon is always going to be 1. So we can say 1, 2, 3. We could also say 1 isopropyl, but that gets a little confusing, so I'm just going to keep it like this. So our total is going to be 5. We'll say 1 bromo, 2 methyl propyl decane. Yes, or you could do it like what he said. You could say 1 bromo. You would have to specify 1 isopropyl. Well, that sort of gets confusing because I don't know if that sort of works because now you have like you don't really indicate that there's a 3 carbon chain. But in this one, you indicate that there's 3 carbons on this complex side group. And one of them is 1 bromo, 2 methyl. So I think this is the correct way to say it. So you say 5, 1 bromo, 2 methyl, propyl, decane. The decane is from the 10. And this propyl right here is indicating that there's 3 carbons in our complex side chain. For the second one, what I would do is I would first translate it into a line angle. Yes, Tran, do you have a question?
Oh yes, for the number 2, is that possible that I can say 2 dimethyl? Or because when I look at the for number 2, right, it's just like 2 ranges. Let's look like 2 dimethyl. Can I say that?
Oh, I see what you're trying to say. No, because we still want to keep our original rules of drawing out the longest carbon chain. So we still have our longest carbon chain as 3. So it's 1, 2, 3. Right. So we don't want to say 2 dimethyl because we can make a 3 carbon chain.
Thank you.
Okay, so for the next one, we're going to, I would say, convert first into a line angle. So we have our 2 chiral centers here. We have a hydrogen pointing outward. We have a bromine like so. And we have a CH2, CH3 like this. We have a CH3 this way. We have we have this isopropyl group, and then we have hydrogen in the back. So let's do it a little without the wedges and dashes so you can see all the bonds clearly. So it looks something like this. Okay, so this is how it looks like without any wedges and dashes. So what do you think is the longest carbon chain? It's going to be this one here. 1, 2, 3, 4, 5, 6. Okay? So we know this is hexane. So now, do we start, my question is, do we start from this side over here or this side over here? Do we start at 1 or do we start at 2? Good, we start at 1 because methyl is in the second position, but bromine is only in the third position. So because methyl comes first, we're going to start at 1. And so we're going to say, we're still going to put bromine first. So we'll say 4 bromo, 2, 3 dimethyl hexane. Okay, now, are we finished? No, because the last part we're missing is we need to indicate R and S. I removed them to make it the diagram a little simple, but now we need to go back and figure out the chirality around each chiral center. So I want you guys to take a second. Tell me what the chirality around number 1 and number 2 are. Okay, so let's check 1. We have 1. So this is a carbon, this is a carbon. But this carbon has a carbon-hydrogen connection, while this carbon has 2 carbon connections, but this carbon only has 1. So this is going to be 2, 3. So it actually looks like this one is going to be S. You are correct in saying that 2 is R, but do you understand why? Do you understand why 1 has to be S, right? Because I'll do it again just to clarify. Right, hydrogen is a dash, so we don't have to reverse it. So this is 1, this is 2 because there's more carbon connections. So it goes like this, and hydrogen is a dash. So how we're going to say this is the bromine, and this is the other chiral center. So we'll say 3R, 4S. So the full name is 3R, 4S, 4-bromo, 2,3-dimethyl hexane. Okay, does everyone get that? Okay, I'm going to clear the board just because I need some more room for the following questions. So I'm going to give you guys a second. Okay, for the next one, it's asking us to draw. You go from the name to line angle. So first I'm going to look at how many carbons. So the first one says octane, so I'm going to draw 8 carbons. Yes, the recording will be on YouTube in about maybe 3 hours. And so you can get, if you want to find it on YouTube, you can go to the peer tutoring channel. I can post a link in the chat in a bit if you want, if you can't find it. But the recording will be available. Okay, so octane will be 8. So I'll do 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. I drew one more. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 carbons. And so now let's figure out what we need. We have an ethyl in the 6th position. I'll say 1, 2, 3, 4, 5, 6. And we have 2 methyls in the 3, 3 position. Like so. Okay? Going from name to line angle isn't as confusing as going from drawing to name. So for the next one, we notice it doesn't matter, because if I started from over here, I would do if let's say I did 1, 1, 2, 3, 4, 5, 6, 1, 2, 3, right? It's just this, but like rotated. It's the same thing. It doesn't matter like when you're naming it, but specifically for this, you can start at any end and it will give you the same result. This is specifically for going from a name to this, to a line angle. Okay. Either end works as long as you keep the numbering consistent. So now we're going to do a cyclopentane. So that will look, first we're going to draw out the pentane molecule. Okay, so now it says 1 isopropyl, 3 methyl. So I'll just start really anywhere. I could just make this my 1 position, so this is 1 whoops. Sorry, I don't know why my pen did that. So this will be the 1 position. And so this can be, we'll go 1, 2, 3, a methyl right there. A lot more simple than just going the other way around. Okay, does that make sense for everyone? So now we're going to do some cyclohexane practice. So the question asks us to convert the following line angle drawing of a cyclohexane molecule into its most stable chair conformation. So what that means is that we want our biggest group, in this case, this isopropyl group, in the equatorial position. So I'm going to say this is equatorial, axial, equatorial, axial, equatorial. So now I'm going to say this is the equatorial up position. So this is up. So it goes axial up, equatorial up. But because bromine is now a dash, this is going to be axial down. It goes back to axial up, equatorial up, but because the methyl is once again a dash, it's axial down. So when I draw it, we'll put equatorial in any up position. So I can put it like this. So 2 carbons away, the bromine is going to be down, like so. And 2 carbons away, the methyl is going to be down. Will the dashes and wedges always be? It depends on how you want to do it. Because I could have said, oh, this is going to be an axial position. Let's say it's going to be axial up. But then I would have to do a ring flip because we don't want the isopropyl group in the axial position. So I made this the equatorial, right? I said this is always going to be, this position is going to be equatorial. And because it's a wedge, I'm going to say wedges mean up. Or sorry, wedges mean it matches what I'm saying. So I'm saying this is going to be the equatorial up position. So because it's a wedge, it stays the same. So it's going to be equatorial up. The next position has to be an axial up. So if it's a wedge, it's good, it matches. If it's a dash, we're going to do the opposite. So the opposite of an axial up is an equatorial down. Okay. Yes, you just need, this sort of needs a lot more practice to sort of like understand why this works, but in this case, what I did was I wanted this to be equatorial, so I'm going to start off by making it equatorial, and everything else around it, I just had to make sure it matches, okay? So now, let's move on to the next question. This question is asking for the molecule in 3 different ways. We have a line angle, Newman, and a Fisher. So first, let's draw out the line angle. So we have a pentane, so it's 1, 2, 3, 4, 5. So it says 3 chloro, 2 fluoro. So we have a fluorine here and a chlorine there, and a methyl like so. It also gives us chirality. So we need to make sure that this fluorine and chlorine are S. So let's determine that before I give it a wedge or a dash. So if this is 1, then we'll say this is 2 because it's going to have a chlorine attached. 1, 2, 3. This is giving me an R configuration. So because I want it to be an S, I'm going to put the fluorine in the wedge position. So now let's do the same thing for chlorine. This is going to be a 1. This is going to be a 2. This is going to be a 3. So that's R. But because I don't want it to be R, I want it to be S, we're going to do like that. So our drawing looks like this. Oops, sorry. Okay, everything good so far? So next we have to convert this into let's do a Fisher projection first. So if we do a Fisher projection, first I'm going to draw out my 2 chiral centers like so. Next, I'm going to put the 2 end groups. So we have if we highlight our chiral centers, we have this chiral center here and this chiral center here. So we have CH3 as one end group, and the other end group is actually going to be the isopropyl group. I'm going to say CH3, 2. And so this occurs because this group right here is not chiral, so it's not part of the chiral center. Okay? So now we need to figure out whether fluorine is going to be on the left or right side. So let's pretend I put it on the left. If I do that, then it's going to be 1, 2, 3. So that's going to be S, but because the hydrogen is right there, it's going to be turned into R. So I want the fluorine right here and the hydrogen here. Now let's do the same thing for chlorine. If chlorine's over here, this is going to be 1. All right, just delete some stuff. This is going to be 1. This up here is going to be 2. This is going to be 3. So that's in the R, but because hydrogen is on the side, it's going to be flipped to an S. So chlorine is going to go right there. Okay. So now our last thing is the Newman projection. So once again, I'm going to go start from the line angle. So we're going to have our eyeball here looking like this. And so we know our down position is this group, the CH3. And our up position is going to be this group right there. So we have that down. Next, we need to figure out if fluorine is to the left or the right. So because we're looking at it from here, and fluorine is a dash, that means it's going to be on the left side. So we have fluorine here, and hydrogen opposite. And so because chlorine is also a dash, they have to be both on the same side, right? You can't have two dashes on those opposite sides. So this is going to be chlorine. This is going to be hydrogen. Okay? Does everyone get that so far? All right, so now let's move on to R and S chirality. So I'm going to give you a sec and tell me what the chirality of this bond of carbon is right there. Okay, so we have one answer for R. Does anyone else disagree? Okay, so let's figure it out. So one is obviously going to be oxygen. Two, we have a carbon and a carbon. So we have to look at the next ones. So we have a carbon connected to two carbons and another carbon. And we have a carbon connected to a nitrogen. So because the nitrogen has a higher molecular weight, we're going to do the number 2, number 3. So this is going to be R. Okay, so now let's say this one over here. We have this one is going to be 1, nitrogen is 2, carbon is 3. So because hydrogen on the wedge, 1, 2, 3, that is going to be S. We'll do the same thing here. We have, it looks like we have a hydrogen on a wedge. So the first group is, this one's actually a little tricky because actually they're all carbon connections. So let me erase some stuff and we can try and figure out which carbon has the first priority. So this carbon here, this one's a carbon, this one's a carbon, this one's a carbon. This carbon is connected to hydrogens. This carbon is connected to an oxygen, and this carbon is connected to 2 more carbons. So because it's connected to an oxygen first, this is going to be number 1 priority. The next one is going to be here, and last one's going to be here. So it looks like R, but because hydrogen is on a wedge, it's going to be S. So we have 2S chiral centers on that. Okay, so now our last question is we're going to indicate pairs of, we have pairs of compounds. We need to figure out if they are going to be isomers, or they're going to, like what type of isomer are they? So we have constitutional, enantiomers, diastereomers, meso, identical, or none of the above. Okay, so I'm going to give you guys a second just to look at A and tell me if you think this is what type of isomer it is. Okay, so we have one answer for A is identical. All right, so let's work through it. First, we need to convert this into a chair structure. So if we follow our rules and say this is axial, let's say this is equatorial down. Because I know we want oops. Right, that's another way to think about it. But just for some practice, I'm just gonna work through it. Like let's say we're converting it. So because we want this group to be equatorial, we'll say equatorial down, because down matches the dash. So this next one is axial down, equatorial down. But because it's a wedge, that means it's the up position. So now it's going to be axial up. So when we draw it out, we have this axial up, 1, 2, equatorial up. So now we know that they're identical. Good. What about B? Do we think they're identical or enantiomers? So the best way to do this is we need to figure out the chirality around each carbon center, because these are two chiral molecules. So for the first one, we're going to number it 1, 2, 3. So it look S, and because the hydrogen is up or on the dash position, that means it's S. For our next one, we're going to do the same thing, 1, 2, 3. This now looks like R, and because hydrogen is on dash, this is R. So we have S and R. What type of isomer is this? Good. So those are going to be enantiomers because they have all the chiral centers are opposite configurations. Okay, let's move on to the next one. What do you think C is? Yes. Do you want to back here? Yeah, so sorry. If I go back, when I move forward and back, it erases my work. But what did you have? Did you have a specific question about something? Oh, okay. Actually, this whole packet is going to be sent to you in about a few hours with the answer key. Okay, so you don't need to take pictures right now if you don't want to. Yeah. So now, tell me. I'll ask the question again. What is C? Do you think it's an enantiomer, diastereomer, meso? What do you think it is? Good. It's a diastereomer because we have chiral centers, but if we notice that only one of them flipped, this one here didn't flip, right? So this has same chirality. Chirality. So because one's the same and one's different, this is now a diastereomer. Okay, good. What about D? What do you think D is? Do you think this is an isomer at all? Maybe it's like neither. Okay, we have one answer for none. What does everyone else think? Okay, so let's go over this. So at first glance, yes, Emily, good. These are constitutional isomers. And so you can sort of tell that they might be constitutional because they both have 1, 2, 3, 4, 5 carbons and 1 OH. So we need to check the hydrogens to make sure, right? So this has 2 hydrogens, 1 hydrogen, 2 hydrogens, and 3 hydrogens. So this has a total of 2, 4, 6, 10. And I'm not including the OH hydrogen because I'm just gonna I can see the OH hydrogen there, right? So the next one we have 1 hydrogen, 2, 2, 2, 2. So that's 2, 4. Am I missing a hydrogen? 1, 2. Oh, sorry. This actually has 1 hydrogen. So it's 9 hydrogens, and this one also has 9 hydrogens. An easy way that I can tell is, so this is our 1, 2, 3, 4, 5. So another way I could tell this was a constitutional is I realized that they had the same carbon and OH. So instead of counting all the hydrogens, I know that this has 1 degree of unsaturation and this also has 1 degree of unsaturation. So because they have the same degrees of unsaturation, that means they're going to have the same hydrogens if the carbons and everything else is exact, right? This can work in a lot of different ways too. If I drew a 6-membered ring and I put 2 double bonds, this also basically translates to this. It's the same thing right there. And I could add an OH, and that would be the same thing, right? The degrees of unsaturation stayed the same. Okay. So now for the last question, what type of isomer are these two? Good. That is a cis and trans isomer, and so we know that when it's cis and trans, those fall under diastereomers. Okay, so that is the whole packet we have. Does anyone have any questions about this packet, about the review, anything you want to talk about? Because we do have about 15 minutes until 2 o'clock when this whole thing ends. So does anyone else have any questions you want to practice?
I'm sorry, do you mind to give me the meso example and the constitutional isomer example?
Okay, sure, we can go over that.
Thank you.
So let's do meso. So meso happens because there's symmetry. So if I have a molecule like this, there are two chiral centers right there. This breakout room right now is encoded in the recording. Any other ones aren't, but this one specifically is. So we see that this has chiral centers in these positions, right? Because we have wedges and non-identical groups. But because that there is a line of symmetry right here, that means this is meso. Because they're symmetrical, meaning that they're superimposable. Okay? So that is meso. Constitutional is sort of easier to see. So this means same formula, different bonding. So if I have something like this, 1, 2, 3, 4 carbons, and I put an OH here, this formula is C4H 8, 9 OH. And if I drew it like this, sorry, not like that. If I drew it like so, like that, this is still C4. We have 3 H's here, 3 H's here. So it's still C4H9OH. So the formulas are the same, but they look different, right? Because they have different bonding. So that's what we sort of mean by this is a difference in constitutional and meso. Okay, does anyone else have any questions? All right, if no one else has any questions, that is the end of this review session.